Okay. So history of the database timeline, I will quickly go through this thing. Obviously, you don't have to remember history of databases. But the important thing is happened in 1970-72 when Cord proposes the relational model for databases. Okay, so this is the first model that become famous. Obviously, before that there were some other models, network-based models, some other database models, but the relational model is the one that has changed the total all the things about databases. And then in 1976, like we have ERM thing, and in early 1980s, Oracle was the first commercially built software. Okay, in 1980s, in early 80s, but by early 1990s, many database companies were down. Only the Oracle was the company which survives because no one was using databases thing. The only thing that you can see in the next slide, the main thing was internet, because at that time there was no internet. You cannot connect your databases from NUIG to your house. So people are just using flat file systems. They are using CSV files. They are using some sort of Excel files, not Excel, but some sort of CSV files, right? So they don't need databases if they cannot access data outside the premises, right? So, but in 1990s, when there is in mid 1990s, when there is a discovery of that internet thing, obviously, then obviously in late 1990s, people do appreciate the applications of databases, and there were so many companies investing in databases. And then in early 21st centuries, there was solid growth of database-based applications, right? So this is the internet, which becomes a main starting point, or due to which database would become famous, right? Obviously, like Facebook or Twitter or Google search engine and all the stuff, they are all using different databases, right? So in the start, DBMS was simple, like you have to write code for each your one database, okay? So here, just like in the last lecture, I told you about the computing concept abstraction. Second most important concept of computing is generalization, okay? Just remember that in computing, there are two very, very important concepts. Abstraction, hiding details from the user. This is abstraction, okay? Make it so simple, like just like in a car, when you are driving a car, you don't even know how that brake system, ABS, or some sort of gear or automatic transmission works. You don't have to need, no need to know each and everything about it, right? But you can still drive a car, because this is abstraction, because that brake or that accelerator is providing you a abstraction point. Behind, all the details are hidden from the driver, right? So this is the thing, that if your application, if you are making some application in computer or for businesses, if it's not providing good abstraction, obviously no one will use. It would be more complicated. Okay, so there are so many mega $1 million projects which were failed because they were very difficult to use, right? So abstraction. And the second good thing about computing, or the concept, is generalization. Remember, in mathematics we have some equations, y is equals to x plus 1. Not difficult equation, very simple, right? X plus 1, and then x, we can put any number from range 1 to 100. What is this? This function of y is equals to x plus 1 is generalization function, in which you can put any value of x and you can get answer, right? Same is the case with your calculator. Your calculator is a very good example of generalization. You can get square root of 2, you can get square root of 222, 21. So this is a generalization of that functions, different functions in calculator, right? So here the problem was generalization, because for every data file, you have to write a separate code for saving that data file. Then they think about generalized access methods. Okay, they said, okay, all the applications should only communicate with that generalized access methods, And then that generalized access method would provide some sort of generalization and abstraction to the operating system, to the hardware, to your hard disk, and it will solve some problem, right? So this is the birth of DBMS-2 version 2. But then it evolved to this sort of thing. Okay, all the applications would be communicating with database management system, DBMS, and it would have some shared database, and it will manage all the hardware, how to communicate networks, and how to operating system things, all the stuff. Okay, so now we don't have to concern about so much concern. Obviously, for fine tuning or for research point of view, we do have some concern how our data is storing in the database and all the stuff. But as a manager, but as a business analyst, you don't have to worry so much about that, how your data would be stored in the particular sector of the hard disk, or how you will get that data. So all the stuff, this will be done by database management system. So data model is a collection of concepts for describing the data in a database. Okay, so data model, so like how we will store our data. So from here we can say that we have different data models: relational data models, key value pair, graph databases. They are also getting very famous, graph databases, right? Document base, column family, array matrix, and the last two, third, or even last three were the old data models. Nowadays they are not, people are not using that network type data model or hierarchical or multi-value. So in this course we would be learning relational data model. So in relational data model, they have some set of rules how we can collect our data, okay, in short. So DBMS is a large integrated collection of data. Models are real world enterprise in which we have entities, okay. This is a very important concept about entities. Students, courses, faculty members, classrooms. These are the entities, important entities that NUIG people want to store information about that, right, in their database. These are the important entities. And obviously for business to business, these entities would be changing. Might be for one university, students are there, courses are there, but they don't have so much, they don't want to store information about their auditoriums or their classrooms because of any reason, okay. So these are the entities. So remember, each database is a mini world. In each mini world we have entities. From that requirements document you will analyze, okay, for this sort of database you need this entity, okay. And like these entities could be students, courses, and we have discussed this thing that one entity in one database could be only a one attribute in another database, okay. It depends on your need. For example, I discussed this thing that for your parking permit, I only require your car registration number, that's it, okay. So for me, for NUIG people, car is not an entity, it's just an attribute of a student or staff, okay. But for some sales company who are selling cars, car is an entity, because they have to note down all the attributes, how many doors, how many seats, what is the capacity of engine, right, what is the model and color and all the stuff. So it means that these entities, or how we can decide entities, dependent on the proposal or the requirements of the document or requirements of your system. In your system might be one entity, but in some scenarios that thing would be only a one attribute, very simple attribute. He has a car, yes or no, that's it. But in other way, might be government tax office, they do know, they want all the information for motor tax or for NCT thing, they require all the information about your car, okay. So it depends So it depends how we will decide entities in the mini world. So we have entities, and then we have some relationships about their entities. Okay. So in a mini world, each entity must have some relationship with at least one another entity. Okay. If one entity is existing in the mini world and it has no relationship with other entities, then it means that it's not a related entity, right? That related information and relationship, you know, that same word coming from the same root. Okay. So if you are modeling a real world database, you have to define entities and their relationships. So we can build one example here, like considering building a course management system. Entities would be students, courses, professors, right? These are the entities. Who takes what course or which course? Who teaches what, right? What are these? Relationships. Good, right? So we have entities, and we have to define relationship with these entities. And how we will define these relationships and all the stuff? From our requirements document. Okay, it will tell that each student needs to enroll in some particular courses, or each faculty has to teach 2-3 courses, right? So these are the requirements. Or in other words, simple words, we can say that these are the business rules, right? You are BIS people. So business rules. These are the business rules which are defining your entities, which are defining your relationships. Every company has different business rules. Okay? So you cannot fit same database which was built for NUIG for some UCD or some other university. Okay? Because they have different business rules. Might be they have different entities. So because of obviously they would have overlapping entities and relationships. Might be 80-90% rules and all the stuff would be same, but still you have to make 100% according to the needs of the user. Okay. Third thing that is very important in relational databases, first is entities, their relationships. Third is attributes of each entity. Okay, characteristics, variables, you can say that, but the attribute is a technical name in databases. Features, you can say that features as well. So each entity would have its own attributes, features, characteristics, right? So again, will you store all the features of entities or only the relevant or needed features? In university CMS, for a particular student, will we store that this student has this particular laptop? Do we require? Or color of the laptop? Obviously no, right? So again, these attributes would be dependent on the on our requirements document. For particular entities, the only important features we would be storing only important features, not all features. Okay. So might be we don't have any concern about storing weight or height of a student in LMS. To teach MS 218 course, I don't need your height or weight, but it's your feature, right? But might be if you are taking membership of some gym or something, might be they have to store your feature that, so that they can track your progress after 3 or 4 months. Okay. So for a particular scenario, you have to decide entities, their relationships, and their attributes. So for each attribute, you have to think about that this attribute is according to the business need or not. Might be in near future, might be you need that, then you can put that feature. Okay, so you have to decide, because you know that if you, let's suppose like many people or sometimes students do ask why we have to care about number of features and all the stuff. Just imagine how many accounts of Facebook are there. 2 billion. 2 billion users, right? And if they have only one extra feature that they never use, and and that feature was like taking on 1 MB on the hard disk, so you can multiply 1 MB into 2 billion. It means that how much storage Facebook would be wasting for only one feature. Okay, and obviously if you have so many big databases, then obviously when you are retrieving that database, you are using your network's bandwidth and data and all the stuff. So you have to be careful about selecting attributes of the entities as well, because it will cost companies in terms of time, in terms of storage, in terms of network communication. Okay, so so for students, entity like student name and registration number would be an important feature or attribute that we can store in a course management system. Any question? Entities, their relationships and their attributes of each entity, you have to define. If you can define very well these three things, then you can make a good design, database design. Okay, because if there is some issue in designing, obviously you have to make these design into a physical database. You have to implement this design, right? So good design will result in a good database application or software. So these are the attributes of the student's entity. Then we have relationships, who takes what or who teaches what, right? These are the relationships. So in a relational model, a relation is an unordered set that contain the relationship of attributes that represent entities. Okay. So a relation, in database we also call this thing as table, okay, one table. So a relation is an unordered set. All of you know that what is a set? Unique values. And unordered, it doesn't mean that which value comes first in a particular row, right? So this is an unordered set. Just like if you have Excel sheet, right, and you have data in different rows, so if there is no issue or concern according to the ordering, then it's unordered. Okay, like row 1, you can copy paste row 1 to row 10 or row 10 back to row 1. It's unordered set. Okay, order doesn't matter in database as well. So here is one relation we have, in which its name is artist. So it has 3 attributes: name, year or country, right? And we are storing information in this relation. So this is one example of one relation, because we are considering relational model. So in a relational model, we start from a table or relation in which we are grouping some data, right, row wise. Or this row in database, we can call this row as a tuple. Okay, a tuple is a set of attribute values in the relation. So this data or this row is one tuple. Okay, how many tuples are there in this relation? 3. Okay, yeah, 3 tuples, 3 rows, not difficult. So basically this is the cardinality of this relation, 3. Size of this relation, okay? One row, one tuple. Just like in your Excel sheet, one row, which contains different attribute values. All of you know Excel, right? So one row, one tuple, and we can say that, like, it's not equivalent to Excel row, but it just for explaining to you is, that's why I'm saying that. Like one worksheet is one relation, okay? Rows and columns. So one row is a one record. In books, you can, instead of tuple, some books say record, one record, okay? One row, one record. And how many attributes in this relation? 3, right? Artist is a relation, and in which we have 3 attributes: name, year, and country. In relational model, there is a very important concept about one thing, that is a primary key. Any idea about a primary key? Unique, good. So every unique key could be a candidate for primary key, but not necessarily it would be a primary key, because in some scenarios you would have many unique keys in a relation, but you have to choose one key, one attribute, one or more attribute combination. You can make a combination to make a primary key. In short, from simple English, what is the purpose of a key for a room? Okay. So, so every room has one unique key, like to unlock this auditorium or classroom. Similarly, in a relational model, you have a key to identify your particular row, your particular tuple, okay? So you can identify, so that you can identify, okay, if I am saying about, I am talking about some particular student, then he or she must have some unique key. In your case, it would be your, your student ID or your registration number. That attribute is your unique key to identify you from other students, okay? Similarly, in a databases, we have for a particular relation, a relation's primary key uniquely identifies a single tuple, right? All of you have PPS number as well. Is it unique? But why are NUIGs not using PPS number as a primary key of you people? Although that PPS number is unique and can identify you as a unique person, but that NUIG ID has more hidden information, that which batch you are relating, or a particular year on which you are starting or ending, or some sort of thing. So that's why they are not using your PPS number. But for HSC people or some other people, PPS number would be more important than your NUIG. They don't ask you, okay, give me your NUIG ID instead of PPS, okay, for some service. So it depends according to the need of the system. It may contain your PPS number, might be, I don't know, NUIG people ask your PPS number at any stage or no? No, okay. On admission forms or any other, no, okay. But for me as an employee, I do have to provide my PPS number as well, but I also have my employee ID, right? So in a relation, it could be possible that you have different unique attributes, but you have to decide which unique attribute or set of attributes would make a primary key of this relation. Clear? Okay. So here in this table, Can anyone tell which could be the unique or primary key of this relation out of these three? Name. It means that in the whole world no artist could have same name.
There's no primary key, right?
Yeah. So from this data only, we cannot say that there is a primary key here. Okay, right? Because name could be repeat, right? Could be same for different artists. Someone is living in US, someone is living, even in US you can find, or in Ireland you can find different actors or different artists who have same name. Even surnames are same, right? So for database you need same thing, right? So you need one unique ID, so you can simply auto-generate some sort of IDs, 1, 2, 3, 4, 5, some incremental sort of IDs, okay? So this is a primary key. Any question? Then another concept is foreign key, and don't worry if you are not getting most of it. This is not the end of this relational model. We have to discuss this thing for the whole course. So, but we have to think like what are the entities, relations, tuples. So we would be speaking this thing or using this thing many times. So don't worry if you don't get all the concepts, okay? But must know that what is a primary key, right? Why do we need primary key, okay? Then another key is foreign key, okay? So foreign key, in these two tables, we have two tables, artist, which contains information about the artist, and you can see there is a one ID for each artist. It would be unique for each artist. And then there is another table, album. Obviously, we are storing someone's information, or we are calling him or her as an artist because he or she has some album, right? So for ID 11 album, can you relate this tuple or row with the link? Can you link this? How you can link these two relations? Can you see something?
The artist attribute.
Sorry?
The artist, the OD number and the long.
Good, good. So it means that like this 1, 2, 3 artist, for this thing we have to go back to this table, this relation, and all the information we can get from here, right? In the manual system, when there was no computers and all the stuff, we have some sort of registers, big registers in which we would be logging all the stuff, and might be all the information would be in the same page. But in computers, we don't repeat information again and again, only. So that's why we are just putting this ID 123 here, okay? So it means that this row or this tuple is linked with this tuple, okay? And by using SQL, we can easily connect these two tables and get data and display it. Okay, for this particular artist, it has like, he or she has like 10 albums named as this. Okay, so this is the concept of foreign keys. A foreign key specifies that an attribute from one relation must map to a tuple in another relation, right? So what we are doing is that we are linking this tuple with this tuple. For this thing we require foreign key. Here 123 is a primary key of this table or this relation, but here 123 is a foreign key, okay? So who will explain what is a foreign key in simple words? So it is a key which will link two tables. It is a key which was or which would be definitely a primary key in some other table. These are the properties of foreign keys, Okay. So yeah, we will discuss this thing in the next lecture in detail, but just definitions. Primary keys are the keys which are uniquely identify tuple in a table, and foreign keys are the keys which are linking two or more tables. Okay. So yeah, here things are more complicated, but I would skip this thing. Okay, this is just a, you can read. So last thing about this lecture is physical data independence, and we can see because of DBMS abstraction and generalization thing, applications should not need to worry about how data is physically structured and stored. Okay, your web browser applications, your Android apps or iOS apps have no concern how this data would be retrieved from the hard disk, how it would be stored. Okay, so this is physical data independence. That's why you can develop complete graphical user interface without considering or without having any information about the database thing, right? If you have some design about database, okay, you can build some graphical user interface on top of that. Application should work with a logical data model and declarative query language. This is important. So your applications would be communicating with DBMS through SQL. That declarative query language is SQL. Okay. So if your user interface want to communicate with DBMS, they will simply communicate through SQL. And SQL has a standard. It contains simple keywords, and it's very easy to use. Like it has some, it has many functions and all this stuff. So leave the implementation details and optimizations to DBMS. The single most important reason behind the success of DBMS today is physical data independence. Okay. So database development process, it contains 3 steps, only 3 steps. Conceptual data modeling, database design, and then you have to build your database. 3 steps. Okay. Conceptual data modeling, then logical modeling, we can say that database design, on paper work. These 2 steps or these processes are on the paper, right? But obviously this build process is physically, you have to build your database or your store values in the DBMS. Okay. So we will start in the next lecture from this thing, what is conceptual data modeling thing, and how we can design a good, how can we make entity relationship diagram, right? ERD diagrams. And we are making this entity relationship diagram from business information requirements. This is the thing that I was talking about before, that from where we will get how many entities I need for this database, what would be the attributes of these entities, what would be the relationships of these entities, right? So all of this information would come from business information requirements. Once we have business information requirements, then we will start making ERD, okay, or conceptual data modeling. And after conceptual data modeling, we will go to the second phase, designing of database, which is also known as in the books as logical mapping. First one is conceptual mapping, second one is logical mapping, and the third one is physical mapping. But in terms of, because I'm using most of the nodes from Oracle course, so they have just different things to explain, which is good because they are talking about in terms of commercial or business. Actual, they are the people who are using or making databases. So I think, yeah, but the concepts are same.